So, that was your quick background into the principles behind structural engineering. This background will help you to converse more easily and more confidently with structural engineers when you're in practice. Now, the last topic we will discuss for this week will be looking at how we trace loads through a building. And we'll be looking at one-way structural framing only for now. Later, when we discuss concrete, we'll introduce the concept of two-way systems as well. But for now, the process of tracing gravity loads through a one-way gravity system is fairly simple. And again, we'll pull over our cartoon set of steel drawings. So, in a one-way system, the floor deck carries the load to beams, which carry the load to girders, which carry the load to columns, which direct the load toward the foundation. So we end up with this hierarchy of components. And for now, we're going to be focusing on these middle three. Now, when we have uniform loads across an entire floor, we can easily determine the amount of load that each element will carry using tributary widths for beams and girders, and tributary areas for columns. For example, if we zoom in on one bay, and we focus on this beam here, we know that half the uniform load on this side of the beam will travel to the beam that we're looking at, and the other half will travel to the adjacent beam. And the same thing occurs on the other side. And so our tributary width equals the beam spacing. And we obtain the linear load on the beam by multiplying the area load by the beam spacing. And of course, the same concept applies to girders and for columns. We simply look at the adjacent component in the same hierarchy on all sides of our member and take half the distance. Now, what happens if our load isn't uniform? What if, for example, we have a piece of mechanical equipment applying an area load like this? And suppose a portion of this area load spills over this last beam. However, the distance that it extends is not greater than the tributary width that we looked at earlier for this beam. So it may be easy to fall into the trap of thinking that none of the load will go to the next beam, and all of it will be applied to this beam, because it fell into this tributary width. However, that is not the case. Tributary widths and areas should only be applied when the load is uniform across the entire area of influence of that member. An area of influence is the area surrounding a member where an applied load will have an effect on that member. And the simplest way of calculating area of influence is again by looking at the next adjacent member in the same hierarchy of components, but this time we will be taking the whole distance rather than half. And so if we look at this beam here, the next adjacent beam is this one here on this side, and this one on this side. And so its area of influence looks like this. And we can see that in fact there is some load that falls into that area of influence. Area of influence is also important to know because it is how we calculate live load reduction. And live load reduction is something that I have seen tested for on the ARE. So let's quickly just talk about the concept of live load reduction. If we look at this beam here and consider the amount of area that it supports, its area of influence, we would be referring to this box here. And again, the dimensions are off the screen, but this is 20 feet. And this is also 20 feet. And so to calculate that area of influence, we have 20 divided by 3 spaces times 2 spaces times 20 feet in length gives us 267 square feet. And so live load, as you can recall, is occupants and their possessions. So what are the chances that this area is going to be completely filled with people and their possessions, this 267 square foot area? Well, it's not really that large of an area, so chances are actually pretty high depending on what type of building this is. However, if we zoom out and look at a different component, let's take this interior column here. The area of influence for this interior column, on this side we're going to go to the next adjacent column, again the next adjacent column, on this side the next adjacent column, and lastly on this side. And so we end up with an area of influence like this. And if we calculate that area, 30 feet plus 20 feet times 20 feet plus 20 feet, we get a much larger area of influence. And keep in mind that this is 2,000 square feet per floor, and this column is carrying 3 floors. So really this should be 6,000 square feet for the area of influence for this column. And so what are the chances that this entire area on all 3 floors is completely filled with people? Well, the chances of that happening are relatively slim. And so that's where the concept of live load reduction comes into play. And here we see the concept of uniform live loads introduced in the IBC. And it has a formula given down here, where the reduced live load is going to equal the original live load times 0.25 plus 15, and then they give this square root of KLL times AT. And this KLL times AT is our area of influence. For some reason, the IBC likes to define it in terms of tributary area, and then they give you this KLL factor to multiply your tributary area by in order to get area of influence. But personally, I find this method to be a little confusing, especially when you have irregular grid spacings or irregular column layout. It can get very confusing with these factors. So instead, it's a lot simpler just to look at what your area of influence is and calculating that directly and not worry about this KLL factor. And of course, there is also a maximum amount of live load reduction that you can apply. So you can see here that it states that the reduced live load shall not be less than 50% of the original live load for members supporting 1 floor, and for members supporting 2 or more floors, it shall not be less than 40% of the original live load. So let's again look at our column and calculate the reduced live load for this column. Again, I'm going to draw out our area of influence. And that area of influence was equal to 6,000 square feet. And say we have a uniform live load of 100 pounds per square foot. So our reduced live load is going to equal that 100 pounds per square foot times 0.25 plus 15 over the square root of 6,000. And that gets us 44 pounds per square foot, which is of course not less than 40% of the original 100 pounds per square foot. And so this is our final reduced live load. Of course, there are some stipulations for when you can and cannot use live load reduction. And again, those are in the IBC. So for example, for heavy live loads, and that would be live loads that exceed 100 pounds per square foot, those live loads shall not be reduced. And so that concludes our second set of lessons for week 1. So with that, good morning, good afternoon, and good night, and I'll see you next time.